Imagine a spacecraft, forged from alloys unknown to human science, drifting silently through the cold, dark vacuum of the interstellar void. It has traveled across light years of empty space, surviving the radiation of pulsars and the crushing gravity of binary stars. Its destination is a vibrant, glowing marble hanging in the darkness, a world of deep blues and swirling whites. To us, this is the cradle of life, a paradise of liquid water and gentle breezes. But as the visitors descend into our upper atmosphere, their sensors begin to scream a warning that defies everything they know about habitable worlds. Within seconds of contact, their hull begins to pit and smoke. Their biological seals start to dissolve. To the rest of the galaxy, the Earth is not a garden. It is a planetary-scale acid bath. We have spent decades looking at the stars, wondering why no one has come to visit us. We assume they are hiding, or perhaps they simply don't exist. But what if the truth is much more unsettling? What if our planet's greatest feature is actually its deadliest weapon? For centuries, we have viewed our atmosphere as the ultimate life support system. We breathe the air without thought, feeling the cool nitrogen and life-giving oxygen fill our lungs. Scientists have long been fascinated by how perfectly tuned our world seems to be for our existence. We call it the Goldilocks zone, not too hot, not too cold, but just right. We search the heavens for Earth-like planets, assuming that our chemical signature is the universal gold standard for biological success. Yet, the more we learn about the chemistry of the cosmos, the more we realize that Earth is a radical, violent outlier. Our atmosphere is a corrosive geochemical anomaly that would dismantle organic travelers the moment they touch the soil. We are effectively living inside a high-energy chemical furnace, thriving in conditions that the rest of the universe avoids at all costs. To understand why we are so dangerous, we have to look back at the Earth as it once was, a world that would be unrecognizable to us today. 3 billion years ago, our planet was a peaceful, methane-rich sanctuary. The sky was not blue, but a hazy, pale orange. The oceans were deep green, rich in iron. Early life thrived here, but it was a slow, quiet existence. These primordial organisms lived in a reducing environment, one where oxygen was practically non-existent. In this ancient world, the chemistry was stable, predictable, and gentle. This is the state that most scientists believe defines normal life in the universe. In the vast majority of habitable worlds, methane, hydrogen, and carbon dioxide form the baseline of existence. But then, something went wrong. A group of microscopic rebel cyanobacteria developed a new way to harvest energy. They began to use sunlight to split water molecules, releasing a byproduct that had never been seen in such quantities before: free oxygen. At first, the planet tried to defend itself. The oxygen was absorbed by the oceans and the rocks, rusting the very crust of the Earth. But eventually, the planet could hold no more. The oxygen began to leak into the sky, sparking the Great Oxygenation event. It was the first and most devastating mass extinction in history. For the anaerobic life forms that ruled the world, this new gas wasn't fresh air. It was a lethal pollutant. It was a corrosive fire that tore through their delicate membranes and shattered their DNA. What scientists discovered about this transition would change everything we thought we knew about our place in the cosmos. The peaceful methane haven was gone, replaced by a volatile, reactive nightmare. Yet this was only the beginning of our transformation into a planetary fortress. Today, our air is composed of roughly 21% free oxygen. To us, this is the breath of life. To a visitor from a methane-based world or a planet rich in noble gases, our atmosphere is a screaming chemical alarm. Oxygen is a scavenger. It is an element that desperately wants to bind with others, and in doing so, it destroys the very foundations of carbon-based life. It relentlessly dismantles organic bonds, turning complex proteins into ash and water. We don't realize it because we have evolved trillions of tiny microscopic repair mechanisms to survive this constant bombardment. But we are effectively living in a slow-motion explosion. What happens next surprised everyone who began to model alien arrivals. We often imagine aliens stepping out of their ships, taking a deep breath, and marveling at our forests. In reality, an alien physiology evolved in a standard galactic environment. A reducing atmosphere would likely undergo spontaneous combustion the moment they were exposed to our air. The chemical potential between their internal biology and our external atmosphere would be so great that the reaction would be instantaneous. They wouldn't just struggle to breathe, they would oxidize. They would, quite literally, catch fire from the inside out. But the danger isn't just in the chemistry of the air, it's in the weight of it. Our atmosphere is dominated by nitrogen, a heavy, stubborn gas that exerts a crushing pressure on everything it touches. For a human, 14.7 pounds per square inch feels like nothing. But for a visitor from a planet with a thinner, lighter atmosphere, perhaps one composed of helium or neon landing on Earth, would be like diving to the bottom of a dark, heavy ocean. The mystery of why Earth is so uniquely hostile became even deeper when researchers began to look at the bends on a planetary scale. If an interstellar traveler were to enter our gravity well, the sudden shift in atmospheric weight could cause catastrophic gas embolisms in their tissues. Their very blood or whatever fluid transports their nutrients would begin to bubble and boil. As we look toward the future, the data from the 2026 spectroscopic readings of the Habitable Worlds Observatory has confirmed a terrifying suspicion. Our blue marble glows in the infrared spectrum like a neon "keep out" sign. Our atmospheric volatility is so extreme that it can be detected from light years away. To an advanced civilization, the presence of free oxygen and high-pressure nitrogen is a biosignature of toxicity. We are the Extremophiles of the galaxy. We have moved into a house that is perpetually on fire, and we have learned to love the heat. To the rest of the universe, we aren't the lucky ones. We are the survivors of a chemical death trap. The spacecraft's airlock cycles, a hiss of pressure equalizing between the sterile interior and the wild blue world outside. On the other side of that titanium door lies a landscape of breathtaking beauty, verdant forests, crashing waves, and a horizon that seems to stretch into eternity. But for the traveler waiting to step out, that air is not a gift. It is a death sentence. To understand why, we have to look past the colors in the clouds, down into the molecular chaos of the Earth's atmosphere. We have been taught to view oxygen as a gentle companion, but in the cold language of chemistry, it is a predator. It is a hyperreactive element, a scavenger that spends its existence trying to steal electrons from anything it touches. This is the corrosive power of our world, a hidden violence that would turn a first contact into a biological catastrophe. But what happened next surprised everyone who studied the kinetics of alien biology. Most life in the universe likely evolves in what scientists call a reducing environment, places rich in hydrogen, methane, or ammonia. In these worlds, molecules are stable. They don't go looking for a fight. But on Earth, the Great Oxygenation event turned our world into an oxidizing environment. This means our air is essentially a slow-burning fire. When we breathe, we are performing a controlled internal explosion to extract energy. However, an organism that evolved without the specialized multi-layered antioxidant defenses that Earth life possesses would find our air as caustic as concentrated lye. The moment the alien traveler steps onto the grass, the oxygen molecules would begin to collide with their outer membranes. To the visitor, it wouldn't feel like a breeze. It would feel like being immersed in a bath of invisible acid. The mystery became even deeper as researchers modeled the oxygen fire. Organic chemistry is built on carbon-to-carbon bonds. In a methane-based life form, those bonds are delicate and tuned for efficiency. When free oxygen encounters these bonds, It doesn't just sit there. It attacks. It shatters the molecular chains, turning the alien skin, sensory organs, and respiratory tissues into oxidized waste. Essentially, they would begin to rust and dissolve in real time. Within minutes, the very structure of their body would lose its integrity. It is a terrifying irony. The very gas that allows us to build skyscrapers and fly jets is a chemical buzzsaw that would shred any visitor from a more peaceful corner of the galaxy. Yet this was only the beginning of the assault. Even if a visitor could somehow shield their biology from the corrosive touch of oxygen, they would still have to contend with the sheer, crushing weight of our sky. We exist at the bottom of a massive ocean of gas, a heavy mixture dominated by nitrogen. To us, the air feels weightless. We move through it with ease, never feeling the 15 pounds of pressure pressing down on every square inch of our bodies. But this pressure is a geochemical outlier. Many of the most likely candidates for life in the galaxy moons like Enceladus or planets orbiting red dwarfs have much thinner atmospheres or are composed of lighter, noble gases like helium or neon. What scientists discovered would change everything about how we envision an alien landing. When a traveler from a low-pressure world enters Earth's atmosphere, they aren't just dealing with gravity, they are dealing with a nitrogen pressure trap. As they descend, the increasing weight of our air would begin to force gases into their liquid tissues. It is the same phenomenon human divers face, known as the bends. But for an alien, this wouldn't be a localized pain in the joints. It would be a planetary-scale decompression sickness. As the heavy nitrogen of Earth is forced into their alien biochemistry, it would form catastrophic bubbles in their equivalent of a circulatory system. Their vessels would rupture, their internal organs would expand and fail, and their neurological pathways would be silenced by gas embolisms. The mystery of our planet's hostility is not just in what the air is, but in how much of it there is. We are living at a pressure that would literally implode the delicate structures of life forms evolved on smaller, lighter worlds. They would see our atmosphere not as a sky, but as a crushing, heavy shroud. But the most chilling realization comes when we consider the lethal biosignature. For decades, we have broadcasted our presence to the stars through radio waves, but our most powerful signal has been silent and chemical. Every time a distant alien astronomer points a spectroscope at our solar system, they see a spike in the data that sends a chill through their understanding of biology. They see the oxygen-methane disequilibrium. In a normal, safe world, oxygen and methane shouldn't exist together in large amounts. They should react and disappear. The fact that Earth has both in abundance tells the universe that something violent is happening here. It tells them that our planet is a high-energy, volatile engine, a place where life has weaponized the atmosphere. To a galactic observer, Earth doesn't look like a place to visit. It looks like a biological hazard zone, a world where the chemistry is so aggressive that it creates a natural barrier, a forbidden planet that no sane traveler would ever dare to touch. How is this possible? How can we thrive in a place that is so fundamentally lethal? The answer lies in our own history as Extremophiles. We are the descendants of the survivors of the Great Oxygenation Betrayal. We have spent billions of years building suits of armor at the molecular level. We have evolved enzymes like superoxide dismutase just to keep the air from killing us every second of every day. We are the monsters who learn to live inside the furnace. But for anyone else, the blue marble is a terrifying corrosive fortress, a world protected not by shields or weapons, but by the very air we breathe. For decades, we have looked at the pale blue dot with a sense of fragile humility. We see a lonely, delicate speck of dust in the cosmic dark. But if we change our perspective, if we look through the eyes of an advanced extraterrestrial civilization, the Earth doesn't look fragile at all. It looks like a glowing ember in a dark room. It looks like a warning. What scientists discovered about our planet's light would change everything. When we look at a distant star, we look for the chemical fingerprints of life. We look for water, for carbon, for warmth. But when the rest of the galaxy looks at us, they see a chemical signature so volatile, so fundamentally broken, that it signals the environment of extreme danger. This is the mystery of the lethal biosignature. In 2026, the deployment of the Habitable Worlds Observatory provided us with a mirror to see ourselves as the universe sees us. By capturing the faint light filtered through our atmosphere, the observatory confirmed that Earth's chemical makeup is a screaming anomaly. In the vast majority of habitable worlds, the atmosphere exists in a state of chemical equilibrium. Gases are stable. They don't react violently with one another. But Earth is in a state of permanent high-energy disequilibrium. We have massive amounts of free oxygen coexisting with methane and nitrogen. In the cold logic of the cosmos, these gases should have neutralized each other eons ago. The only reason they haven't is because of the relentless, aggressive engine of Earth's biosphere. But what happened next surprised everyone who studied these light fingerprints. To a distant observer, this disequilibrium is a sign of high-energy life. It tells them that whatever lives on Earth isn't just surviving. It is actively terraforming its planet into a high-octane chemical reactor. To a species that evolved on a calm, methane-shrouded world, this isn't an invitation to visit. It is a sign of a biological fortress. They would see our oxygen-rich sky and realize that any landing would require shielding far beyond their technology. Our atmosphere creates a natural barrier, a chemical wall that prevents non-oxidizing life forms from ever making planetfall. Expert perspectives suggest that this is the missing piece of the Fermi paradox, the question of why we haven't met anyone else. We have always assumed the silence of the universe was because life is rare, but the evidence suggests a much more haunting possibility. Life is common, but we are the outliers. Most life in the universe likely exists in reducing environments, cool, stable, and gentle. To them, Earth is a caustic outlier. They don't avoid us because they are indifferent or hostile. They avoid us because our home is a geochemical nightmare. We are like the deep-sea tube worms that live near volcanic vents, thriving in a heat and chemistry that would melt anything else. Yet this was only the beginning of the realization. If an alien species were brave enough or desperate enough to attempt a landing, they would encounter a survival paradox. To walk on our surface, they wouldn't just need a spacesuit. They would need a mobile containment unit capable of resisting extreme oxidation and crushing pressure. Think of the specialized equipment humans use to work inside nuclear reactors or deep-sea trenches. That is the level of protection a normal alien would need just to take a stroll through a park. The Great Oxygenation Betrayal didn't just kill off ancient Earth life, it effectively fortified the planet against the rest of the galaxy. The mystery of our survival becomes even more profound when we realize that we are, in a very literal sense, combustion-powered beings. Every breath we take is a calculated risk. Our cells have evolved to handle the free radicals produced by oxygen microscopic shrapnel that tears through biological molecules. We have turned a poison into a fuel. This high-energy lifestyle allows us to have complex brains, fast movements, and rapid evolution. But it comes at a price. We are living fast and burning bright. To an alien observer, we must look like creatures made of fire, living inside a world of acid. But what scientists discovered next was the most unsettling revelation of all. This atmospheric toxicity isn't a permanent state. It's a temporary, violent phase in a planet's life. Eventually, all planets tend toward equilibrium. Our oxygen-rich atmosphere is a geochemical explosion that has been frozen in time for a few 100 million years. We are living in the middle of a planetary-scale reaction that hasn't finished yet. Yet this was only the beginning of our understanding of Earth's unique role as a galactic outlaw. We aren't the standard for life. We are the extreme exception. As we look up at the stars, we see a universe of possibilities. But the universe looks back and sees a chemical death trap. We are the residents of a fortress made of air, protected by the very elements that we think of as our greatest gifts. How is this possible? How did a small, rocky planet become the most hostile environment in the known sky? The answer lies in the peak revelation of our own evolution. A story not of peace and harmony, but of a violent chemical victory over the very nature of the universe. If an interstellar traveler were determined to breach our atmospheric wall, they would have to approach Earth not as a destination, but as a hostile combat zone. We often imagine men in black or secret government facilities hiding alien craft. But the most effective containment facility on the planet isn't a bunker. It's the air itself. To survive even a few minutes on our surface, a visitor from a standard galactic environment would require a containment suit of staggering complexity. It would need to be a mobile, hermetically sealed fortress, capable of resisting the relentless stealing of electrons by our oxygen-rich air. To them, our breeze is a blowtorch. What scientists discovered about the requirements for alien survival on Earth would change everything we thought we knew about first contact. Imagine the engineering. The suit would need to be coated in non-reactive ceramics or noble gas-infused alloys that simply don't exist in a nature that hasn't been fire-tested like ours. Every joint, every seal, every sensor would be under constant chemical assault. But the mystery became even deeper when researchers considered the internal environment. The alien wouldn't just be fighting our chemistry. They would be fighting our pressure. Their suit would have to act as a deep-sea submersible, maintaining a low-pressure, methane-stable internal atmosphere while being battered by the heavy, nitrogen-rich ocean of our sky. If a single seal were to fail, the result wouldn't just be a leak. It would be a biological flash fry. The high-pressure oxygen would scream into the suit, meeting the alien's low-energy biochemistry and triggering a spontaneous microscopic inferno. Yet this was only the beginning of the horror. Even if the traveler remained perfectly sealed, they would be functionally blind and deaf to our world. Our atmosphere doesn't just corrode biology, it filters and bends light and sound in ways that would be alien to a creature from a thinner, calmer world. To them, our blue sky wouldn't look like a ceiling. It would look like a thick, glowing fog of high-energy radiation. Our sounds, the rustle of leaves, the roar of a waterfall would hit their sensors with the force of physical blows due to the sheer density of our air. To walk on Earth would be to walk through a crushing, screaming, acidic hallucination. This leads us to the most mind-blowing discovery of all the peak revelation. We have spent decades searching for extremophiles in the boiling vents of the ocean floor or the frozen wastes of Antarctica, marveling at how life can survive in such hostile places. But what if we have it backwards? What if we are the ultimate extremophiles? In the eyes of the galaxy, the boiling sulfur vents aren't the extreme. Our air-conditioned living rooms are. We are the creatures who have mastered the art of living inside an explosion. We have built our entire civilization on the foundation of a chemical reaction so violent that it defines the very limit of what biology can endure. But what happened next surprised everyone who modeled the galactic mean. If most life in the universe is anaerobic and exists in low-pressure, reducing environments, then humanity represents a biological superweapon. Our bodies are packed with high-energy ATP, fueled by the most aggressive oxidizer in the periodic table. We move faster, think quicker, and heal more rapidly than almost any other hypothetical life form. We are high-octane organisms. To a visitor from a peaceful world, a human being wouldn't look like a fragile biped. We would look like a frantic, high-energy monster that can survive in a bath of acid and a furnace of heat. We are the fire breathers of the cosmos. Yet this was only the beginning of the realization. This high-energy status explains why we are so restless, why we have covered our planet in steel and glass in a mere blink of geological time. We are fueled by the very toxicity that keeps the rest of the galaxy at bay. Our atmosphere is a great filter that has worked in our favor. It has kept us isolated, yes, but it has also acted as a protective shield, a planetary moat that no one else can cross. We aren't the lonely children of the universe. We are the kings of a fortress that everyone else is too terrified to enter. How is this possible? How can a species be so oblivious to its own lethality? We look at the blue marble and see peace. The universe looks at us and sees a geochemical bomb waiting to go off. But the mystery of our existence has one final haunting chapter. What happens when a species that thrives in a death trap finally decides to leave it? What happens when the monsters of the acid world decide to bring their fire breath to the rest of the galaxy? The realization that Earth is a planetary-scale fortress changes more than just our understanding of alien contact. It changes our understanding of ourselves. We have spent centuries looking for our place in the cosmic hierarchy, often placing ourselves at the center of a grand, welcoming community. But what scientists discovered about our unique toxicity would change everything. If the rest of the galaxy views our atmosphere as a lethal acid bath, then we are not the hosts of a grand welcoming party. We are the inmates of a high-security biological prison, thriving in a cell that no one else dares to unlock. Yet this was only the beginning of a much deeper mystery. As we begin to reach out into the stars, we aren't just sending scouts, we are sending infection. Every time we launch a probe to a moon like Europa or a planet like Mars, we are carrying the corrosive legacy of Earth with us. Even if we sterilize our spacecraft, the very chemistry of our technology, the metals forged in our oxygen-rich fires, and the materials designed to withstand our crushing pressure, is a foreign, aggressive force in a peaceful universe. We are the Extremophiles now venturing into normal space. When we eventually step onto another world, we won't be the fragile explorers we imagine. To a native life form evolved in a stable, methane-rich environment, a human astronaut in a pressurized suit wouldn't look like a hero. They would look like a walking biological hazard, a creature from a world of fire and acid, threatening to leak its toxic atmosphere into their sanctuary. The bigger implications for humanity are staggering. If we are the only ones capable of surviving in a high-energy, oxidizing environment, then we possess a biological superpower that we are only beginning to understand. Our restlessness, our rapid technological advancement, and our ability to thrive in extreme conditions are all symptoms of our high-octane biology. We are the galaxy's fire starters. We have evolved to turn poison into progress, and that makes us the most unpredictable variable in the cosmic equation. But it also means that the great silence, the Fermi paradox, might not be a sign of a dead universe, but a sign of a quiet one. A universe that is watching us from a safe distance, waiting to see if we will ever burn ourselves out or if we will bring our furnace to their doorstep. What scientists discovered would change everything about our future. Our status as outlaws means that any future galactic federation might not be a club we are invited to join, but a containment zone we have to navigate. We are the monsters under the cosmic bed. Yet this was only the beginning of the irony. Our blue marble, the icon of peace and environmental fragility, is actually a screaming chemical warning sign. It is a terrifying, corrosive fortress that has protected us for billions of years, allowing us the solitude to grow, to learn, and to eventually look back at the stars. The mystery of our existence has led us to a peak revelation. We were never meant to be normal. We are the descendants of a biological coup, a group of survivors who turned a global extinction event into a planetary reign. We don't just live on Earth. We are part of its aggressive, defensive shell. Our fresh air is a volatile chemical weapon. Our gentle breezes are the currents of a heavy, crushing ocean. And our sunlight is the fuel for a slow-motion explosion that powers our every thought and movement. As we look up at the night sky, we should stop wondering why they haven't come to save us, or why they haven't come to lead us. The truth is much more profound. They aren't coming because they can't survive us. They aren't coming because our home is a nightmare of reactive gases and crushing weights. We are the aliens of the universe, living in a world so hostile that it is its own best defense. We are the kings of the acid bath, the masters of the furnace. And as we prepare to leave our fortress and head out into the quiet, stable dark of the cosmos, we must ask ourselves one final haunting question. When the rest of the galaxy finally sees the monsters coming, will they see us as explorers or as the greatest threat they have ever known? The pale blue dot is not a sign of our vulnerability. It is the armor of our world. And in a universe of shadows and stability, we are the ones who carry the fire.